Hello, everyone. It's my pleasure to speak here. I'm Bo Zipeng from Ant Group. Today, I'd like to share our exploratory work on GraphIG framework named Subgraph Retrieval enhanced by graph text alignment for Commonsense question answering. This paper was completed in collaboration with Peking University. Before I begin, I want to introduce some background information. First, I will talk about Commonsense question answering, short for CSQA. CSQA is a crucial task in natural language understanding that requires reasoning according to common sense knowledge. Existing CSQA datasets generally adopt multiple choice questions to evaluate the model's performance. Here is an example. Where is the capital of China? A. London. B. Beijing. C. New York. D. Shanghai. E. Guangzhou. And the correct answer is B. Beijing. The main challenge of CSQA is it is difficult to learn common sense knowledge solely from pre-training text corpus, as it is really expressed explicitly in natural language. Therefore, many works explore the incorporation of knowledge graphs. Knowledge graphs are more efficient in representing common sense and can aid PLMs in comprehending QE pairs and enhancing reasoning capabilities. Existing KG augmented works primarily follow a paradigm that first extracts relevant subgraphs or paths related to a given question based on predefined rules and then models the extracted structural knowledge. Despite their success, previous approaches still have several limitations. The first limitation is the subgraph quality. The subgraph's quality suffers when retrieved through simple string or semantic matching, posing limitations for subsequent operations. And the second limitation is graph text misalignment. The misalignment between graph and text encoders presents a challenge for PLMs to internalize the knowledge contained in the acquired subgraph, leading to reduced task performance. And the last limitation is the uncontrolled subgraph size. To obtain sufficient relevant knowledge, the number of nodes in the subgraph will expand dramatically with the increase of hop count, raising the burden of the model. Next, I will detail the motivations of our method. To address the limitations of rule-based subgraph extraction methods that may overlook critical nodes and result in uncontrollable subgraph size, we propose to retrieve subgraphs from a constructed subgraph vector database. To ensure complete neighbor information for each node and avoid the blockage of the message passing mechanism of GNNs caused by pruning edges linked to marginal nodes, we propose a BFS-style subgraph sampling method. Finally, to overcome the challenge of misalignment between graph and text encoders, which undermines the effectiveness of knowledge fusion and impacts task performance, we propose a bidirectional contrastive learning method. Here is the model architecture of our SEPTA. First, a bidirectional contrastive method is proposed to align the semantic space of graph and text encoders. With the encoders aligned, we transform the knowledge graph into a subgraph vector database and introduce a query enhancement strategy for better subgraph retrieval. Finally, all the information retrieved is combined by an attention mechanism to bolster the reasoning ability of PLMs. Next, I will provide a detailed introduction to each module in SEPTA. The first step is graph text alignment. The motivation of this step is coordinate the embedding spaces of graph and text encoders and fully harness the respective strength of text and KG. The alignment step can be divided into 2 steps, including generating training graph text pairs with equivalent semantics, and employ a bidirectional contrastive learning method to train the encoders of both modalities. In this slide, I'd like to introduce the construction progress of graph text pairs. First, we propose a BFS-style sampling strategy for subgraph construction, which initiates from the central node and proceeds to sample neighbors hop by hop. Then, we textualize the subgraphs to construct synonymous text descriptions. We first convert all relation links into triplet descriptions. Specifically, we map each relation type to a relation template and concatenate the head concept, relation template, and tail concepts and the description of each triplet. Finally, we concatenate all descriptions to compose the final description. After constructing graph tag pairs, we propose a graph text contrastive learning method to align the semantic spaces of text and graphs. First, JNN and PLM are utilized to encode the knowledge subgraphs and natural language descriptions to obtain the corresponding representation. Then, to project the knowledge subgraph embedding and text embedding into the same semantic space, 2 linear projection layers are designed as follows. To avoid the loss of inherent knowledge caused by overfitting of the PLM, only the JNN and the linear projection layers are trainable during actual practice. Finally, we employ InfoNCE with in-batch negative sampling to align representations of 2 modalities bidirectionally. Then, we will introduce the subgraph retrieval module, which includes 3 steps, that is, subgraph vector database construction, query enhancement, and subgraph retrieval. First, we want to introduce the construction of the subgraph vector database. We first adopt a BFS-style subgraph sampling strategy, which is the same as the graph text pairs construction, leveraging the analogy between BFS and the message passing mechanism of JNNs. Then, for each subgraph, we obtain its graph embedding and text embedding and combine them to form the subgraph vector. Finally, we construct a subgraph vector database with all subgraph vectors. However, direct use of QA pair embeddings and queries may not align well with the pre-trained corpus, affecting retrieval accuracy. Therefore, we retrieve question-related triplets from the KG and concatenate them with QA pairs. Specifically, we first apply entity linking to find entities in the question and options, and retrieve triplets containing these entities. Then, we concatenate the retrieved fact triplets with the question and options. Finally, we use the align PLM to encode the concatenation into a vector, which serves as the enhanced query for subgraph retrieval. With the enhanced query, we retrieve relevant subgraph vectors from the subgraph vector database based on the cosine similarity. We finally recall the top k subgraph vectors with the highest similarities. The final stage is the prediction of the answers. We first integrate the retrieved subgraph vectors through multi-head attention. Then we add the integrated representation and the enhanced query and feed them into a linear layer to predict the score of the option. Since some questions are expected to be answered based solely on the question context, we also encode the QA pair directly to infer the score without additional knowledge. The 2 scores are finally weighted and summed to yield the final score. We conduct experiments on 5 datasets. The first dataset is Commonsense QA, a 5-way multiple-choice QA dataset, including the official split setting and the in-house split setting. For the official split setting, the ground truth of the test set is not publicly available, so we submit our model's predictions to the official leaderboard to evaluate the test accuracy. The second one is open book QA, a 4-choice dataset to evaluate the science common sense knowledge. And the third one is social IQA, a 3-choice dataset to evaluate the understanding of common sense social knowledge. The fourth one is PIQA, a 2-choice QA dataset regarding physical common sense. And the last one is riddle sense QA, a 5-choice QA dataset about common sense riddles. The statistics of 5 datasets are shown in this table. We use accuracy to evaluate all baselines and our model. We evaluate SEPTA on Common Sense QA and Open Book QA. We use Robota Large and the text encoder in Common Sense QA, and use Robota Large and Aristo Robota in Open Book QA. Methods with Aristo Robota use the textual evidence in previous research as an additional input to the QA context. The baselines incorporating actual corpus are marked with the star, such as Dragon and DHLK. From the results, we can find that our method can contribute performance gains to LMs, and our method SEPTA outperforms all baselines without additional corpus on both datasets. And compared to baselines incorporating additional corpus, our method also achieves comparable performance. We also evaluate SEPTA on the official Common Sense QA and Open Book QA leaderboards. Our method achieved results surpassing all baselines based on the identical PLM, and it exhibits comparative performance compared with methods with larger scale parameters, such as the Unified QA. The results on the other 3 datasets are shown in the following table. From the results, SEPTA consistently achieves superior performance, and this observation underscores the overall effectiveness of SEPTA in addressing various common sense reasoning datasets or tasks, demonstrating a unified methodology. We also conduct an ablation study on Common Sense QA and Open Book QA to explore the effectiveness of each component of SEPTA. We remove the alignment process, retrieve subgraph vectors, fact triplets, and scores predicted based on QA pairs, that is, set the lambda equals to 1, respectively. From the results, we can observe that 4 components are all crucial for SEPTA, and removing any parts will result in a decrease in performance. Specifically, the performance drops the most significantly when we remove the graph text alignment, and removing either fact triplets or subgraph vectors will affect the performance. This is because if the representations of graphs and texts are not thematically aligned, then during the knowledge retrieval stage, the retrieved subgraph vectors may be irrelevant and situated in different latent spaces from the textual information. Finally, only using knowledge-enhanced representations for predictions cannot achieve optimal results. To evaluate the robustness of SEPTA, we conduct extensive experiments in low-resource settings with different proportions of training data, including 5%, 10%, 20, 50, and 80 in Common Sense QA and Open Book QA. From the results, SEPTA achieves promising performance in all settings, and it exhibits a trend where the performance improvement relative to other baselines is more significant with fewer training. Finally, we provide a conclusion for our work. First, we propose a novel framework called Subgraph Retrieval enhanced by graph text alignment for common sense question answering. Second, SEPTA reframes the CSQA task as a subgraph vector retrieval problem and introduces a graph text alignment method to enhance retrieval accuracy and facilitate knowledge fusion for prediction. Extensive experiments on 5 CSQA datasets demonstrate the effectiveness and robustness of the SEPTA framework, outperforming SOTA approaches. In the future, our work will concentrate on the following aspects. First, we want to explore more effective pre-training tasks for semantic alignment between graph and text representations. Second, we also want to apply the SEPTA framework to larger language models if sufficient computational resources are available. Finally, we want to extend the SEPTA framework to other related tasks, such as node classification and link prediction on text-attributed graphs. Additionally, I want to promote our latest work on a comprehensive survey of Graph RAG. In this survey, we formalize the Graph RAG workflow encompassing J-indexing, J-retrieval, and J-generation. We also outline the core techniques and training methods at each stage. Additionally, we examine downstream tasks, application domains, evaluation methodologies, and industrial use cases of Graph RAG. Finally, we explore future research directions to inspire further inquiries and advance progress in this field. That's all. Thanks for your listening.
Okay, any questions about as you have questions? Yeah.
Yeah,
Please go ahead.
First, yeah, thank you. This was a great presentation, and it was very interesting for me to see that your experiments confirm that graph text alignment is very important. That's precisely the entity linking task that I was talking about. Figuring out how to link concepts and entities out of text to a graph. And I want to ask you for this common sense question answering task, have you thought of using a pre-existing graph with which bears additional knowledge? Because if graph is extracted from whatever volume of text, it could be that just the domain, the knowledge needed to answer these or questions may not be there. So rather than thinking of extracting graph from text, have you thought of using anything that already exists? For instance, Wikidata.
So you're asking about data alignment. I think you're asking.
I'm asking about alignment that doesn't go to generated graph, but rather using an already existing knowledge graph. For instance, Wikidata.
Okay, thank you for your question. I think first, I think the alignment progress in our paper is very crucial because the semantic spaces of text and graphs is not alignment. And if we remove the alignment progress, the performance will drop. And I think, second, I think the alignment progress is a very challenging task. And recently, several papers also propose the alignment process. And I think we are not solve this task completely. And in this paper, we the alignment progress we propose is a general framework. And it can apply to any graph data. Our method in this paper is very simple. We predefined some rules to transform the links or edges into sentences, and we concatenate all sentences to form a whole description of the graph. And we use the description to align with the graph structure. Specifically, we use the JNN to encode the graph and the PLM to encode the text, and use bidirectional contrastive learning to align them to a unified semantic space.
Yes, I got this. But yeah, this wasn't my question. It was rather, have you thought of using a existing graph to provide with context?
Yes, I use the concept net,
okay,
open knowledge graph about Commonsense. Thank you.
Wonderful, thank you.
Okay.
By the way, you don't need to generate sentences. Most of the LLMs these days, they do understand triples, so you can, when providing these subgraph, you can also just prompt the LLM that I'm giving you these triples, and put subject, predicate, object to source, type, target, and it's gonna work. It could be even a bit more compact as compared to generating sentences. But that's just a possible optimization. Thank you.
Thank you.